Hi, my name is Yuval, and I'm a postdoc at the University of Michigan. The title of my talk is Towards Reliable Data-Driven Decision Tools. Automatic data-driven tools are widely used these days in many application domains, in particular tools that are used for decision making. The increasing use of those tools also leads to many cases of algorithmic bias and discrimination. For example, a tool developed by Amazon to filter out uh, job candidate resumes was discriminating against women, or an algorithm that was used to grade students instead of exams that were canceled due to the pandemic turned out to be biased against high achieving students from low income families, like a native Spanish speaker who failed their Spanish exam. The growing impact of those tools on society and the fact that we rely so much on them brings up questions regarding their reliability and in particular how we can make those tools more reliable. I'm going to present three methods for bias mitigation, whose goal is to increase the reliability of data-driven systems. These tools are designed to address challenges at different phases in the development pipeline. And I'm going to give a high-level description of each one of them and provide references to the relevant papers for more details. The first part of the pipeline is data equation. We know that the data used for data training, for model training, has a significant effect on the resulting model. For example, we know that insufficient representation of minority groups, or on the other hand, skew data, which is extreme representation of some groups, can lead to biased models. For example, the tool developed by Amazon was discriminating against women simply because there were not enough women in the dataset. When selecting or collecting the data for training, data analysts typically apply some data profiling, which is a process of extracting some metadata and useful information that can help better understand data. For example, it can help determine whether the data fits the needs, fits the task at hand. The problem with this process is that it's usually not automated, so it's hard to do well, and it is very time consuming. To help both data scientists and data users in general, the notion of nutrition labels is being proposed, where the idea is to capture in a concise label some dataset properties that can help better understand the data. One important such property is information regarding the counts of attributes value combination, which are different groups in the data. So to help data scientists in the data collection phase, we propose an automated way of generating labels that consist of information about the counts of attributes value combinations. The challenge here is that the number of combinations can be extremely large. So our solution was to select a small subset of those combinations that can help users easily get a very accurate estimation for the representation of each group in the data. Once the data was collected, it typically undergoes some processing and analysis, which helps get high-level understanding of the data. One way to do it is through aggregation queries. As a simple example, consider this dataset of student score in an exam. It has information about the gender, the school, the address, whether it's rural or urban, number of previous failures, and the grade in a scale of 1 to 20. This query computes the um, average grade per address type, and based on the query result, we can see an analyst can come to a conclusion that on average the grades of students with a rural address are higher than the grades of students with an urban address. But if we take a closer look on the data, we will see that this is not the case for female students, which are 50% of the data in this case. And the question is then, how can we assess the quality of the result of such queries? So we propose a scoring method that quantify the quality of a query result. We do it by looking into subgroups of the groups in the query result, and for each such subgroup, we check whether the same trends are present as the original query. Then the score corresponds to the fraction of data that align or agree with the query result. The final step in the pipeline consists of an analysis of the resulting model. One aspect of this analysis is fairness assessment, and there are many ways to define fairness. I'm not going to talk about all of them, just to mention a few. One way to define fairness is through accuracy, where if a given group in the data has extremely low accuracy compared to the other groups or the overall accuracy, we may say that this group is treated unfairly by the model. And similarly, we can look at false positive or false negative errors. When we consider different definitions, we might get different groups that are treated unfairly. So if we continue with the previous example and say we have a model that predicts whether the student pass or fail the exam, where passing grade is a grade above 10. The result of the prediction are depicted here in the prediction column, and we can see that this model misclassified two tuples. One is a false positive and the other is false negative. Now, based on the data in this table, we can say that the accuracy of the model is 0.875. But if we look at students from the GP school with an urban address, we will see a drop in the accuracy, and where they have only accuracy of 0.67. So this group is treated unfairly if we consider fairness as accuracy. If we think of fairness as a false negative error rate, we will find that male students with a single failure are treated unfairly by this model, and they have a very high false negative error rate compared to the overall. The common practice in fairness analysis is that we are given a protected group or groups, which are defined through some value assignment to set of sensitive attributes like gender or race. The problem with this approach is that the groups may be unknown in example. For instance, one of the sources to the bias in the grading algorithm I mentioned earlier was that it used a historical score of the school to make the prediction. But school or school ID is not a natural sensitive attribute. So it's easy to overlook groups that are defined using this attribute when we analyze the fairness of the model. To address this challenge, we propose a method for automating detection of groups that are treated unfairly without the need to predefine protected group or sensitive attributes. And our method can support various fairness definitions, both in classification and ranking. Thank you very much. If you have questions or comments, please feel free to reach out.